Pluto had it coming from the outset. Pluto's trajectory intersects that of another planet. Pluto, the mysterious small planet at the far reaches of our solar system, is generating excitement in the realm of astronomy. Recent reports suggest a possible encounter with Neptune, raising concerns among scientists and space enthusiasts. Prominent figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the implications of this cosmic event. But how did Pluto end up on a collision course with its neighboring planet, and what could this celestial clash signify for life on Earth? Join us as we unravel how something enormous just collided with Neptune and how scientists have been left anxious by this cosmic anomaly. Pluto, once celebrated as a full-fledged planet, experienced a transformation in its status, being reclassified as a dwarf planet due to its peculiar orbit. Despite this demotion, Pluto continues to captivate and intrigue the astronomical community. Recent predictions from distinguished scientists like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's trajectory potentially intersecting with Neptune's, hinting at a looming threat of collision between the two celestial bodies, which could have significant repercussions for Earth. Pluto's journey around the Sun stands out due to its unique characteristics within our solar system. Its orbit is exceptionally lengthy, spanning a staggering 248 years. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun. Adding to its mystique is the highly elongated shape of its orbit, a departure from the more circular paths followed by the major planets. Furthermore, Pluto's orbit deviates by 17 degrees from the ecliptic plane, giving its path a steeper incline compared to other planets. The combination of Pluto's inclination and its elliptical orbit introduces layers of complexity to its orbital pattern. One notable aspect is its periodic intersection with Neptune's orbit. For around 20 years during each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. Delving deeper into Pluto's orbit, it's fascinating to note that it's not a perfect circle but rather an elongated ellipse, resembling more of an oval shape. This unique orbit results in significant variations in Pluto's distance from the Sun throughout its journey. At its closest approach, Pluto comes within about 30 astronomical units, AU, of the Sun, while at its farthest point, it reaches over 49 Australian dollars away, almost twice the distance of Neptune from the Sun. Moreover, Pluto's orbit is inclined at an angle relative to the orbits of the major planets in our solar system. This inclination not only contributes to the complexity of its orbit but also plays a crucial role in its interactions with other celestial bodies, particularly Neptune. When Pluto crosses paths with Neptune, their gravitational tugs influence each other, altering their trajectories over time. The intricate dance between Pluto and Neptune underscores the dynamic nature of our solar system. While Pluto was once considered a lone wanderer in the outer reaches, its close encounters with Neptune highlight the interconnectedness of celestial bodies, each exerting gravitational forces that shape the paths of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movements with greater precision. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer solar system. While the likelihood of a direct collision between Pluto and Neptune remains low, the possibility cannot be entirely discounted, prompting continued monitoring and study by the astronomical community. Despite its diminutive size and distant location, Pluto continues to command attention and curiosity among scientists and enthusiasts alike. The question arises, why hasn't there been a crash between Pluto and Neptune? The answer lies in the gravitational pull from other planets. Astronomers began studying Pluto's path soon after discovering it, and its route puzzled them. Unlike most planets that adhere closely to the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery deepened when they realized Pluto's path intersected Neptune's. Despite these complexities, Pluto's orbit remains stable, showcasing the intricate mechanics of space. Understanding how three celestial bodies move and interact gravitationally, like Pluto, Neptune, and the Sun, is a significant challenge. It's like trying to predict where they'll go based on where they start and how they pull on each other. For Pluto, this challenge reveals how its path, Neptune's path, and the sun's pull all work together. Terms like azimuthal libration, latitude libration, and the VZK oscillation help scientists solve this cosmic puzzle. Azimuthal libration is crucial for keeping planets in their orbits. When Pluto crosses Neptune's path, it's at least 90 degrees away, keeping them from crashing. Latitude libration ensures that when Pluto nears Neptune or other large planets, it's well above their path, reducing the chance of a collision. The VZK oscillation, named after scientists von Zippo, Leo, and Kai, explains why Pluto's orbit seems peculiar but remains steady over time. Despite the chaos in space, some patterns and rules keep things in order. These rules keep Pluto's orbit stable, preventing crashes with Neptune or changes in its path. The idea of orbital chaos, showing how a celestial body's path is very sensitive to its starting position, is well illustrated by Pluto. Even small changes in its position or speed can disrupt its orbit over a long time. Scientists use computer simulations to figure out how Pluto moves in space. These simulations use sophisticated math to replicate how Pluto interacts with other space objects, like Neptune. By tweaking these simulations just a bit, astronomers can see how minor changes can alter Pluto's path. In the late 1980s, these simulations found something intriguing about Pluto's orbit. Even though there are factors that should make it stable, Pluto's orbit can still be unpredictable. Just a tiny difference in where Pluto starts or how fast it's moving can lead to significant changes over many years. But even with all this chaos, Pluto's orbit remains stable for an exceptionally long time, like billions of years. This suggests that even though Pluto appears erratic, its journey around the Sun follows some sort of order. Predicting what will happen with planets like Pluto, which have irregular orbits, is difficult. These systems are so unpredictable that it's hard to foresee what will happen in the long term. Simulations help us get an idea of what might happen, but they also show us that we can't predict everything perfectly. These models need precise starting points and simulate complex factors. Even a tiny mistake can lead to vastly different results, making it challenging to make accurate predictions. Understanding Pluto's orbit is important, especially when we consider whether it might collide with Neptune in the future. This knowledge helps us better understand how our solar system functions. Pluto's orbit demonstrates how orbits that seem irregular can balance out due to gravity and how celestial bodies move in space. It's crucial to keep observing and studying these phenomena so we can grasp where we fit in the universe. When we explore space, we discover that things can be unpredictable, and Pluto's orbit is a great example of that unpredictability. Pluto's orbit is not like those of the other planets. It's more oval-shaped, which means it's not a perfect circle. Sometimes it even gets closer to the Sun than Neptune does. This can create challenges because Neptune is also out there traveling along its path. There's a small chance that Pluto and Neptune could collide at some point. Despite its unusual orbit, Pluto manages to keep its distance from Neptune most of the time. This is due to something called gravitational forces. Gravity is like an invisible force that attracts things toward each other. So even though Pluto and Neptune might seem like they're on a crash course, their orbits are carefully choreographed dances, guided by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What appears chaotic at first glance can be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the intricate mechanics of our solar system. This ongoing observation and analysis are essential for expanding our understanding of the universe and our place within it. Imagine if Pluto and Neptune did collide. It would be a cosmic event, sending shockwaves through our understanding of the solar system. While we've made progress in understanding space, Pluto's situation shows that we still have a lot to learn. Studying how large planets affect Pluto's path gives us valuable insights into how our entire solar system functions. It illustrates that where each planet is and how it moves can influence the paths of other objects in space. Even though space is complex, some leading scientists are concerned that Pluto might crash into Neptune. This raises questions about why this might happen, even though it seems unlikely. Neil deGrasse Tyson, a renowned space scientist, has some intriguing ideas about Pluto. He believes that reclassifying Pluto as a dwarf planet, not a major one like Earth, is a step forward. He thinks we are constantly learning new things about how celestial objects move in space. Tyson views Pluto's unusual path as a sign that there is still much we don't know. He believes that the mysteries of space are what makes studying it so thrilling. He also understands that significant events in space, like Pluto's reclassification, spark public interest in astronomy. Tyson aims to help people grasp the fascinating and sometimes peculiar aspects of space mechanics. He believes it's essential to discuss how space mechanics can surprise us. Tyson collaborates with other scientists to alert the public about the potential dangers of Pluto's unusual path. After extensive study, he's concerned that Pluto might collide with Neptune one day. He suggests that this could pose serious problems for our entire solar system. A collision between Pluto and Neptune would be a rare and serious event. It would release enormous energy and could shatter Pluto. Debris from the collision could scatter through space and impact other planets and moons. Neptune might also feel the effects and change its movement. Noted theoretical physicist Michio Kaku, recognized for his contributions to string theory and science communication, provides a thought-provoking perspective on space exploration. He believes that comprehending the future of space travel and the connection between celestial mechanics and theoretical physics can be gained from examining phenomena like Pluto's orbit. Kaku views Pluto's orbit as a glimpse into the future of space exploration. By understanding the complex gravitational interactions and orbital dynamics of celestial bodies such as Pluto, we can enhance future space missions, facilitate safer navigation through the solar system, predict potential risks, and plan expeditions to distant regions of our cosmic neighborhood. Kaku emphasizes that insights derived from Pluto's orbit can be applied to exploring other celestial bodies, offering a roadmap for comprehending distant worlds. He frequently underscores the profound relationship between celestial mechanics and theoretical physics, stressing that the movements and interactions of planets, such as the gravitational interplay between Pluto and Neptune, are grounded in fundamental principles of physics. Kaku's work in theoretical physics, particularly string theory, aims to unravel these core principles. He proposes that examining the intricacies of celestial mechanics, such as Pluto's orbit, can provide insights into the underlying laws of the universe. Similar to Tyson, Kaku has also pondered the potential collision of celestial bodies, linking it to his theories about the universe. A collision between Pluto and Neptune, though significant in astrophysics, could offer a unique observational opportunity, potentially advancing our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. Such a collision could produce extreme conditions of energy and gravity, revealing the behavior of fundamental particles and forces under extreme circumstances, a central focus in string theory. Additionally, the gravitational waves generated by such a collision could provide valuable data for testing string theory's predictions regarding gravity and spacetime. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications could be profound. Understanding events like this could deepen our comprehension of the fundamental nature of the universe, as articulated by string theory and other theoretical physics fields. Its unique characteristics, influenced by the gravitational forces of nearby planets, particularly Neptune, highlight the intricate and dynamic nature of space. Nevertheless, the universe harbors many mysteries, and the three-body problem is just one of them. Scientists anticipate other potential disasters, underscoring the ongoing quest for understanding and exploration in the vast cosmos. Although it's highly improbable, there's still a slight chance of planets colliding in space. This can occur because planets' paths are influenced by various factors, such as gravity from other planets, known as the three-body problem. In systems like TRAPPIST-1, where 7 Earth-sized planets reside, gravitational forces create a rhythm in the planet's movements called orbital resonances. Over time, these patterns can destabilize a planet's path and potentially lead to collisions. Although collisions are not occurring currently in systems like TRAPPIST-1, scientists monitor these systems closely to understand how planets affect each other's paths, particularly when they approach each other. This helps us comprehend planetary movements in space. Occasionally, rogue planets, which do not orbit a star and drift unpredictably, are present. These planets were once part of a star system but were expelled due to factors like gravity or proximity to another star. Over time, these wandering planets can travel far and might enter other star systems. However, due to the vast emptiness of space, the chance of them colliding with another planet is very slim. Rogue planets are rare compared to the number of stars and planets with stable orbits, making collisions even less likely. When galaxies merge, it can disrupt the orbits of the star systems within them. Although direct collisions between planets are unlikely during these massive events, the strong gravity can alter the movements of stars and planets. Sometimes, planets are ejected into space as rogue worlds, or they may crash into each other or their host stars. These disturbances could even form new celestial bodies or new stars. The late heavy bombardment theory proposes that around 4 billion years ago, there was a period of intensified impacts involving comets and asteroids. This surge in collisions is believed to have occurred because the outer planets, such as Jupiter and Saturn, were moving significantly, disrupting the paths of numerous smaller objects in space. Consequently, these smaller objects were sent onto unpredictable trajectories, many of which ended up in the inner solar system, leading to a dramatic increase in impacts on planets like Earth. Although these collisions did not involve planets crashing into each other directly, they illustrated how gravity can cause substantial changes in space movements. Scientists believe this bombardment influenced the surfaces and histories of planets in our solar system and might have even delivered water and organic material to Earth, contributing to its development. As stars evolve, they lose mass, which can impact the orbits of surrounding planets, sometimes causing them to widen and potentially overlap. This change is most evident in systems where stars are nearing the end of their life cycles. As a star ages and exhausts its nuclear fuel, it undergoes significant mass changes, particularly during stages like the red giant phase or when it sheds material in a planetary nebula. These mass fluctuations can greatly affect the system's gravitational balance, causing nearby planets' orbits to either move outward or become more compressed. This phenomenon is more common in multiple star systems, where complex gravitational interactions can lead to unstable orbits. In such systems, gravitational forces from multiple stars can interact unpredictably, increasing the likelihood of orbital shifts and potential collisions between planets, or with other celestial bodies, or even ejection into interstellar space. Although the actual chance of a planetary collision is considered very low due to the vastness of space and the relatively small size of celestial bodies, these scenarios are of great interest to astronomers and astrophysicists as they provide insights into planetary system dynamics and galaxy evolution. The ongoing study of Pluto's orbit represents the continuous quest for knowledge in space exploration. As illustrated by Tyson and Kaku, each discovery brings us closer to understanding the intricate nature of our universe. It is a journey that challenges our perceptions, broadens our horizons, and inspires future generations of explorers and scientists. Could this collision occur sooner than anticipated? And what could be the effects on our blue planet? Share your thoughts in the comments section. Thanks for watching another episode of Voyager. While you're here, make sure to click the video on your screen for more quality content.